All right.
Floor is yours.
Thank you, Professor Kimijan. So it's my pleasure to show you all the work I've done today during my years of PhD here, where I've investigated effective policies for emergency response to large earthquakes. And I'd like to start by showing you this picture over here, this map, which shows what's the worst disaster per country in terms of number of injured people. The first thing I want you to notice from this plot is the size of the balls. So multiple countries around the world had emergency responses where they have exceeded 10,000 people injured in just one single event. In fact, multiple others have exceeded even the 50,000 people injured in one single event. The second thing I want you to notice from this plot are the colors of the balls. They indicate the type of natural disasters. So from this plot indicates also that earthquakes have been the worst natural disaster in terms of emergency response for multiple countries. And that happens because earthquakes are sudden, they have no warning, and they are unpredictable, they're uncertain. So if we look at this seismic area in Turkey and we observe the box here enclosed in black, we saw there that the last earthquakes were in the 17 and 1800s, and then all of a sudden in the 99 they had the Kokeli earthquake there, leaving an emergency response with 50,000 people injured. So emergency response is a critical issue for communities worldwide, and this motivates the work of my PhD. I think cities, communities need to create more informed, more robust emergency response policies, and for that they need better understanding of two critical things. The first thing is how and where large earthquakes occur, and the second thing is what factors govern emergency response so that they can see how to improve it, how to improve emergency response. And the objectives of my PhD are to bring new insight into those two topics. So first, my first objective is to characterize better large earthquakes recurrence, and the second objective is to design better emergency plans. And when you investigate these two topics, because they are very broad, it's very easy to fall outside the earthquake engineering field, the traditional earthquake engineering field. So you'll see in this dissertation that I've taken an interdisciplinary approach at the intersection of earthquake engineering, seismology, and emergency medicine. That's what I'm going to show to you today. And so I've subdivided the dissertation or the presentation into three main topics. The first two deal with seismic hazard and the recurrence of large earthquakes. The third one deals with the emergency response of cities to large earthquakes. In the first two, first I developed a novel model to characterize large earthquake recurrence. And then in the second part, I'm going to show you how I'm using synthetic computer generated databases to improve the calibration of hazard models. So let's start with the first topic. This is the proposed model for earthquake rupture. And first, let me give you a little bit of background. When I mean earthquake rupture, I mean to propose a model that captures where and when and how big earthquakes are going to be. And I want to tell you that the elastic rebound theory, which explains earthquake rupture behavior, has been around for more than 100 years. It has been proposed by Reed more than a century ago. And just simply put, an earthquake is described as a release of sudden release of energy, a strain, and a stress that the tectonic plate incorporates over the period of time until it reaches to another earthquake again, let's say at year 50. Surprisingly, or maybe not that much, the main applications of seismic hazard do not capture this behavior. They are, in most applications, seismic hazard is calculated with a time-independent model by Professor Cornell, and this model interprets earthquake probability occurrence as if we, for example, have an earthquake happening at year 150. Using this model, the conditional probabilities of having an earthquake at time 50 or at time 150 would be the same. So the earthquake rates are constant over time. However, there are other models that have captured this behavior, and Professor Kirimijan has extensive work on that. Professor Ellsworth, who is also a member of my committee, has worked on that. And these models capture this behavior that tectonic plates can accumulate energy, and therefore implying that the probabilities of an next earthquake occurrence can increase. There are other more sophisticated models that couple these time interactions with space interactions, meaning that in multiple sections of the fault, you can have some time dependencies that are going to interact one with another. Professor Kirimijan has also worked on that, and currently Field is leading the work there in USGS to model time-dependent hazard for California. However, the current models have certain limitations. The existing model has certain limitations. They are, first of all, very complex because they are tracking these complex interactions of space and time of earthquakes, so they are hard to calibrate. There is a lack of robust methods to calibrate the parameters of the models, and in addition, the lack of earthquake data because there are not many earthquakes have long return periods. There is little data to calibrate well the models. So the objectives of my work here in seismic hazard are to first develop a model that captures these implications of the elastic rebound theory over space and over time, to develop a robust parameter estimation technique associated to this model, and third, to supplement the reduced limited data, the historical data, with physics-based computer simulated data sets. So first of all, I'm going to show you how my proposed model looks like. So I'm idealizing a tectonic plate, the contact area of a tectonic plate with a 2D representation as this area that can be enclosed in a rectangle, as you can see here, that then is going to be discretized into a small number of sections, as we were to do it in finite element analysis, for example. And then we describe the time-dependent behavior at each section of the fault using a time-dependent model. In this case, we use the Brownian passage time distribution. And with that, we capture rupture at each time step in the fault. In this case, we use a 1 year time step. So because we're capturing rupture as a Bernoulli distribution, whether the one section ruptures or not, when you look at the whole system, you deal with a multivariate Bernoulli distribution. And this is what we have here. And finally, we introduce also some spatial correlation to incorporate the behavior that ruptures or sections of the fault that are closer together can interact one with another. So one part of the fault can trigger a rupture in a neighboring section. So now let's look a little bit at what is happening at each section of the fault. So because we use this Brownian passage time model, implicitly what we're introducing in each section of the fault is this behavior that you see here. The Brownian passage time distribution can be interpreted also as a Brownian relaxation oscillator, in which stress, for example, can be tracked as two additive components, one that's going to increase with constant rate, plus one Brownian motion that captures some uncertainty. And because there is some uncertainty, sometimes the recurrence, when the stress reaches failure or the threshold, sometimes it lasts 50 years, sometimes in the arrival time 100 years, and there is some randomness in this model. So that's captured with this PDF that you can see here, that it's defined with two variables, the mu, which is the mean return period, and then the alpha, which is the periodicity of coefficient of variation, and you can see the PDF formula also in the bottom. So now, when we look at how the fault behaves, as the whole fault behaves, what you can see is that when we're introducing this correlation behavior, we're correlating also the Brownian motions. So at some times, one section is going to rupture by itself. At some other times, multiple ruptures are going to rupture simultaneously into one single larger event. So that's the basic concept of this proposed model for characterizing the time and space interactions of earthquake rupture. So now we apply the model to the subduction zone in Peru. This is the subduction zone. We can see the trend here in red. It's a big fault, as you can see by the geometry of it, and it's bounded by high creeping zones in the south and northern regions, as inferred by GPS data. Those are the Nazca Ridge and the Mendaña fracture. We collected historical data for the region for large ruptures, including 450 years of data with 12 ruptures larger than 7.5. So we set up the model around this data. We subdivided a tectonic plate into 8 sections, and so that the smallest section corresponds to the minimum magnitude in the historical catalog, as you can see here. So the minimum section is there of around 80 kilometers, which triggers, according to empirical scaling laws, a minimum magnitude of 7.5. So our first step forward to calibrate this model was to do a very simple calibration technique. As you can see in this plot to your left, I'm showing you the earthquake catalog as projections as projections of the rupture area to the strike of the fault. So you're going to see the strike direction in the y-axis and the time in the x-axis here. So we perform a maximum likelihood estimator to get the mu and alpha at each section of the fault, each of the 8 sections of the fault. And then after, we calibrate the correlation length from the spatial correlation to replicate empirical data. So in the plot in the right, I'm showing you annual magnitude exceedance rate. In the x-axis, there is the magnitude, and in black, it's the empirical data from the historical catalog. And you can see that the model under several values of the correlation length is fitting reasonably well the empirical data. So after we calibrated the model here, we use it to model hazard, and we assessed hazard as the probability of exceeding a PGA of 0.4 G in the whole region during the next 30 years. So first, we calculated the hazard using a time-independent component to have a clean comparison, and that's using the Poisson distribution here, and you can see that in the plot at your left in green. And then we use our model to calculate seismic hazard and divided it over the time-independent model just to see the differences. So as you can see, from the center region to the bottom, we have lower predictions of seismic hazard, and that's triggered because the model is successfully capturing recent rupture we had here. We had in 2007, we had the Pisco earthquake in that part of the fault. So the model is capturing this behavior and is reducing the seismic hazard here by 4 times as if you were to compare it with a time-independent model. So we consider that this model can capture this seismic gap behavior. So that concludes the first part of my of this presentation. And for the second one, I'm going to take a little bit of water first. All right. So we're going to leverage synthetic data, computer-generated data, to calibrate better the model. One issue we faced at calibrating this earthquake rupture model was that because we are estimating parameters of the fault separately in all the sections. Sections are not able to share information with one another. So in some sections of the fault, we end up calibrating the Brownian passage time distribution just using one data point, like in section 1, for example. The other complication with this calibration was that the historical catalog is just too short. We are trying to track ruptures that have on average 100 or 200 years, and we just have 450 years of data, which is not as much as we would like to have a reliable calibration of the model. So in order to overcome this problem, we did 2 things. The first one was to develop this Bayesian update, so that instead of updating all the parameters at each section at a time, we calibrate all the parameters simultaneously. So there is the model allows to share some information with neighboring sections. And the second thing was to supplement the limited historical data with synthetic data, physics-based synthetic data. And the schematics of the update is shown at the bottom. So you start with a prior, perform a first Bayesian update using the physics-based synthetic catalog, get a posterior, and then tune more the parameters with a historical catalog to have a final posterior of the parameter. So we've seen how the historical data, where we got the historical data, and now we're going to see how we get the physics-based synthetic catalog. For that, we work with some seismologists. We work with Professor Ampuero from Caltech and with Dr. Galvez from ETH and Dr. Villegas from the Geophysical Institute of Peru. So we set up this model. It's the same part of the subduction fault. You can see the geometry there. We use that rate and state friction law, which describes the behavior of rock mechanics in the tectonic plate, using different cases to tune the parameters of this physics base. We use 3 cases, varying the rate and state friction law parameters. And we use also built into the model 4 asperities, which are the regions where earthquake can start nucleating. And those are the darker areas here in the tectonic plate. And we vary the sizes of the asperities also. We located them where previous earthquakes happened. And we vary, as I'm telling you, 3 cases of the sizes of the asperities. So in total, doing a permutation, we had 9 cases. We simulated 2,000 years of synthetic data for each of these 9 cases. And it's very highly computationally intensive. Running it in the Sherlock supercomputers with 250 processors, it lasted the simulation almost from 1 to 2 weeks, each of the cases. So it's very intensive. These are how the results look like. These are videos that you can see over here of one of the cases. So you can see here at your left, we're tracking shear stress over the 1,000 years, and then to the right, we're seeing how we couple or how we model interseismic coupling that it's released in yellow each time there is an earthquake. So these are how the simulations look like. So now we did perform some validation on the synthetic data, so just to see that they are giving reasonable results. And these are how the annual exceedance rate, magnitude exceedance rates of the synthetic data look like in gray. You can see that there is a lot of uncertainty, or they are sensitive to the tuning parameters. And you can see the historical catalog in blue. So one thing to comment out of the synthetic catalog is that it also has uncertainty, and it's not small. The first source of uncertainty is, or the first uncertainty is in the x-axis, which is the magnitude. Most of this historical catalog comes from the era where we didn't have the deployment of seismometers or seismic instrumentation. So a lot of those magnitudes were inferred from subjective isoseismals that were described over the whole region of analysis. And some people just, based on that, draw where can the rupture be, how long it is, and with that was inferred, the magnitudes were inferred. So that's how this catalog is built before 1940s. So there is a lot of uncertainty in the magnitude direction, in the magnitude axis. And there is also a lot of uncertainty in the y-axis, because we are, if you recall, we're just analyzing 450 years of data. So for events larger than 8.4, we just have 2 earthquakes. So this is defining the whole annual exceedance rate. So the historical catalog also has a lot of uncertainty. Now, the way I interpret the variability in the physics-based catalog in light of this high uncertainty in the historical catalog is as that the synthetic catalogs can bring new understanding, novel understanding for this area in light of these reduced data sets of reduced historical data. And these synthetic catalogs are also reproducing feasible earthquake cycles according to the initial parameters of the model. So we further validated these synthetic catalogs, computer-generated synthetic catalogs, and we utilized first an independent study that was performed at the Geophysical Institute of Peru, where using GPS data, measuring tracking displacements over the whole crust of the coast of Peru, they inferred what was the locking in the tectonic plate, in the contact area. And you can see that it has a complex spatial distribution at the left. So then we compare that with our results, as you can see at the right. And you can see that the high coupling areas in the simulations correspond to where we define the asperities, where the nucleation can happen in the tectonic plate. So even though the spatial distribution of high coupling is quite complex from the GPS data, we were satisfied by the fact that this simpler model, our simulations, roughly match this thick stripe of high coupling in the subduction zone along this strike, and also the high coupling in the deep part of the tectonic plate. So after validating these results with these 2 sources of information, we proceeded to perform our Bayesian update. If you recall, we had in the second step the final tuning with a historical catalog, but first we're going to do the first tuning of a parameter with a physics-based simulations that now I'm going to show to you here. And this is what's happening at each step with the Bayesian simulation. So we start with, that's the formula that describes the posterior given the data. We are dealing with 2n plus 1 parameters, 1 alpha and 1 mu for each of the sections, plus 1 correlation parameter. We start with a simple prior at the beginning, but then when we try to calculate the posterior, this corresponds to quite complex equations. So it's computationally infeasible to solve the integral that you see in the denominator. So in order to overcome this issue, we use another technique, a Markov chain Monte Carlo technique, using a Metropolis-Hastings version of this algorithm, where we're going to have symmetric random walk over the whole parameter space to sample from the posterior. So this is what we did at each step of the calibration. So if you recall, we had 17 parameters in the model. We're dividing the tectonic plate into 8 sections. And now I'm going to show to you what was the prior just for 2 of the parameters. These are 2D slides in a 17-dimensional space. So here I'm showing you mu4 and mu5. So once we perform the first calibration of the model, the first update using the synthetic data, we see that the synthetic data is very effective at reducing the initial high uncertainty in the prior. And once we have the second update with a historical catalog, this technique becomes very effective because it performs a final tuning to the parameters to a new mean and median prior, to new parameter medians. So in order to have a more clean comparison here, I'm showing you what would have happened if you ignore the synthetic data and just perform the parameter update just using the historical data. So the dashed black lines here are showing you what would have happened just with the historical data, and the solid black line here shows the combination of both. And as you can see, there is a very effective reduction in the uncertainty of the parameter estimates. In fact, on average, over the whole section, the reduction in the parameter uncertainty was by a factor of 2. So we propagated these results finally to the seismic hazard. We used the model just calibrated with the historical data here, and this is how it propagates the seismic hazard at the left. And then we use both data sets to propagate the seismic hazard, the results of the seismic hazard at the right. And our variations are incorporating the synthetic data trigger 40% reductions in most of the region. And this, just remember, these are contributions from large earthquakes. So I haven't added the moderate or small earthquakes in these calculations. And I think for with the increase of high performance computing, we're going to have more and more synthetic data. So I think as a community, as an earthquake community, we're going to see more of these plots. And I think it's going to come more to the community to agree how much do you trust in your synthetic data set in light of the large uncertainties and reduce time spans of the historical catalogs. So I think this is going to be quite exciting in the next few years. So just summarizing the contributions of the seismic hazard part, I showed to you how we've developed a new model to capture interactions over time and space of large earthquake occurrence. Show you how we are using synthetic data, how we are proposing this parameter estimation technique that is robust and can leverage synthetic data to supplement the short historical data. And you can see more details of this work in these two papers that are listed at the bottom of the slide. With that explained, I'm going to go to the third part of the presentation, the last one, and I'm going to explain to you how communities can have policies that can increase the performance in the emergency response due to these large earthquakes. All right, I have another pause here, just in case. All right, so I want you to recall the first picture where you saw that emergency responses can have to deal with thousands of people injured. And the critical part about earthquakes is that hospitals usually look like this after a disaster. This is a picture we took in our reconnaissance mission with Professor Miranda here. And this hospital, the state of this hospital was quite dramatic because from a structural point of view, it only had slight damage because it has just a few cracks in some beams and columns, but the hospital was fully evacuated. This is 6 years after the disaster. And it was because the damage in the partition walls and the ceilings scared the patients, so they exited the hospital. And the same with the doctors. So as you can see, this is a critical behavior of emergency response because these are the institutions that are supposed to address the large number of casualties in the city. So with that as a motivation, we examined critical factors, or we revised what were the critical factors in an emergency response in previous earthquakes, and we determined that first, high demand of healthcare services is critical. There is the reduction in the capacity of hospitals, as you saw, but also that hospitals in a large city, in a large urban center, behave as a system, and that has been seen in Christchurch after the disaster, in Chile after the earthquake. Hospitals tend to transfer patients and share resources, so they don't act in isolation. As objectives of this part of my PhD, I've developed a method that captures these three features. I'm also leveraging some optimization techniques to design effective policies for emergency response. And third, I'm applying this method to Lima, Peru. I don't know if you've noticed, but I'm from Lima. So this is the rupture scenario that we are analyzing. We analyzed the 1940 Lima earthquake rupture happening in the subduction zone that we just described. It's a large rupture in comparison to the city dimensions. Lima is a mega city. It has 10 million people there. The last earthquake that was huge was almost 40 years ago, and when the population was only a third or a fourth of what it was today. So nobody has really tested what's going to happen with infrastructure then when the next one comes. We're analyzing a nighttime scenario because housing buildings, housing infrastructure is really critical in Lima as a result of bad construction practices. And I want to summarize first how we model earthquake casualties. So for this, we extended the performance-based earthquake engineering framework from single building to a regional level. The PBE framework is very modular. You start first with ground shaking, then go to damage state, then go to a decision variable. In this case, it's going to be multi-severity casualties. And then you have to face the challenge when you go to a regional state to go from one building to thousands of buildings. So that means that you have to, at the regional level, you have to model ground motions or ground shaking, build a vector over the whole city that has correlations. I have to see how these correlations propagate to the damage state, which is also a vector, very high dimensional, which at the same time propagate to the injuries in this case. And it can be of multiple severities at each house. So conceptually, this is what the model does. There are details in a couple of publications. Here I'm just showing my name, I guess, but there are a couple of publications that mention how this is the formulation gets extended from simple buildings, from one single buildings to multiple buildings, and seeing how you can exploit the variable interdependencies to calculate this with computational efficiency. There are ways to compute this more effectively. So we apply this model, and I wanted to show you, without going into detail, just how the modules work. First, we have the ground shaking module. We analyzed it over a space grid of 1 kilometer by 1 kilometer. We included soil microsonation information, very high resolution that amplifies shaking where soil conditions are worse. We assessed 3 shaking intensities and used some common ground motion prediction equations as well as spatial correlations for the model. In the second module, we analyzed the building damage over the whole region. We analyzed a large amount of data, 1.5 million buildings that were collected a lot in Peru, in Lima, but also summarized by the global earthquake model. We used their fragility functions, 36 structural typologies according to the material, to the ductility properties of the buildings, and we tracked 6 structural damage levels, going from slight damage all the way to complete damage with collapse. Finally, we assessed the casualty modeling, going all up from severity 1 and severity 2, which require basic medical treatment, all the way to fatality. Severity 3 is very critical because these are the injuries that need immediate treatment. If not, they are life-threatening. And we also, out of the analysis, we saw that vulnerable buildings can be real killers because adobe and unreinforced masonry had 20 times more chances of killing people than code-compliant buildings. This plot over here summarizes the focus of this part, the casualties. These are the casualties that need injuries. Talking with our collaborators, in this part we collaborated with Professor Judith Mitrani, who is part of this committee, and also with the physician Celso Ambaren from Peru. We determined that 10% of severity 2 plus 100% of severity 3 could be a good way to quantify how many people we're going to need operating rooms after the disaster. And the results indicate that almost 5,000 people will need this kind of treatment. This is the mean values over the city. And these are injuries like compound bone fractures or the crash syndrome with open wounds and punctured organs. It's very critical injuries. So this is how we model casualties. And now this is how we model post-earthquake hospital functionality. Same, we use very modular analysis, ground shaking, damage state, and then as a decision variable, we model operating room functionality. For that, we use 2 sources of information. First, the damage state, the structural damage state of each building, but also we consider the hospital safety factor that was collected for several buildings for several hospitals in Lima that was proposed by the World Health Organization. And we use those categories as a penalty factor for a reduction in functionality, as you can see here in those ratios. And we apply this formulation, and these are the main results. Well, first I want to describe to you how the data looks like. The Católica University in Peru with the World Bank collected an extensive data sets on the hospitals of Lima. 41 main campuses were surveyed. They were composed of 700 buildings. So we have information of all the seismic vulnerabilities of these buildings. We collected information, we use information of the hospital safety index of these hospitals, and also information of their operating rooms and ambulance resources. And combining all of that information with a framework I showed you before, these are the results of how the functionality ratio is spread over the city here from red to yellow. So now we put both sources of information together. On one hand, we put the demands and the capacities. So first, let's talk a little bit about the capacity of the system after the earthquake, and that's showing the image to the left here. First, the circles in purple highlight or show the sizes, show how many operating rooms you have per hospital distributed over the city. And the first thing I want you to notice is that there is a huge centralization problem. In fact, 56% of the capacity pre-disaster of operating rooms is in only 4 districts, centric districts, which just represent 2% of the total area in the city. And the problem is exacerbated a little bit more after the disaster, because then 59% of the operating rooms are functional at this city center. Now, when you look at the right, at the casualty surge, the distribution looks pretty much the opposite. As a result of poor building constructions in the housing, where most of the residential houses are in the peripheries, there are heavy demands there. In fact, only 13% of the demands fall within those 4 centric districts where the capacity was high. So there is a heavy mismatch between the demands and the capacities of the system. And this is what motivates the third part of this of my emergency response model, which is how we can leverage the system behavior of hospitals to treat patients more effectively. So we proposed this network model in which we represented each hospital as a set of 2 nodes. The first node represents the triage of the hospital. The second node represents the discharge of the hospital. So we can track how many patients are treated over time at each hospital. And also we connected all the triage areas to represent the hospitals can transfer patients from one hospital to another. And this is a very interesting formulation because it allows you to track the flow of patients at each time and decision variables, like who stays at triage, who goes to treatment, who is transferred from one hospital to another. So we apply this model to this region. And what that previous formulation allows you to do also is to write down equations for tracking the citywide waiting time, how long a patient will have to wait till completing treatment in an operating room once the earthquake happened. And also it allows you to track the number of ambulances tripped. So according to some constraints, you can constrain the problem also using some linear equations, using first a very classic flow conservation constraint, and then ensuring as a second constraint that the capacities of the operating rooms or the ambulances are not exceeded at any time. And then we have a third constraint which ensures that the number of people waiting in each triage area is properly represented by a positive number. So we can solve this, fortunately, using linear programming, which there are a lot of packages to solve for this problem. And we use this technique, we use this model to evaluate what would be the performance of different strategies, emergency response strategies. First, we define some low coordination strategies. One we call baseline 1, which is the one that hospitals without operating rooms are going to be able to send patients only to the other closest hospital that is working. That's the baseline 1. The baseline 2, hospitals without operating rooms are going to send patients to the hospital with the highest number of operating rooms, perfectly reasonable strategy. And then we're going to move to higher coordination strategies that I'm defining or calling policies. The first one is going to allow the system to transfer patients across the whole city to any other hospital and to share ambulances. And then the policy 2 is going to introduce into the system 15 operating rooms, extra operating rooms that are going to increase the capacity by 8%. So we performed our simulation using this network model, and this is how the results look like. So let's start with baseline 1 in black. The mean waiting time of a patient in this case is of 30 days. We're still discussing with physicians what are the implications for the health status of people who wait, so what kind of treatment or stabilization procedures should receive. So then remember that this is under this policy, hospitals are sending patients only to the next closest hospital. Now when hospitals send patients to the largest hospital, you see a slide, some reduction in the waiting times to 22. And then when you go to higher coordination strategies, you can see that the waiting times can be more effectively reduced because the system is distributing patients to the whole city. And finally, if we add 8% deploy these field hospitals, we can see that the waiting times get reduced even further. The reduction is just by 2 days because we're only increasing the capacity of the system by 8%. More increases in the capacity obviously are going to decrease the waiting time of patients. So I want you to see first what's happening at each of these policies. Let's start with the baselines. So here I'm plotting the number of people treated at each hospital as with the orange balls, and also the number of transfers across the system in green. If we look at the first baseline, because patients can only be transferred to the next closest hospital, patients are not strategically redistributed in the system. As a result, only 28% of the demand is treated in the center of the city where the resources were 59%. So it's not as effective. And ambulance capacity is a bottleneck. In the baseline 2, when hospitals send patients to the largest hospital, we see that the 2 largest hospitals overflow in the city. In fact, 60% of the patients are treated there, whereas they only have 40% of the capacity. And also roads overflow because multiple hospitals are sending patients to the same hospitals using the same road. The critical problem. In contrast, when we go to the high coordination strategies, we can see that first in policy 1, you're allowed to share ambulances so they don't bottleneck the system anymore. And then second, because you are allowing to transfer patients across the whole city, the demands closely match the capacity of the system. In fact, at the center of the city, when you have 59% of the capacity, you treat there 56% of the demand. So they closely match. And then on top of that, with the baseline 2 strategy, when you add 15 additional operating rooms, you further decrease the waiting time because these operating rooms are strategically located with this formulation at the periphery of the city, as you can see by the balls in dark colors here in the north and the south periphery. And this has another effect in the city, which is that roads overflow a little bit less because the capacity is brought to where the demand is needed the most. So you don't need as many transfers as you used to need with the low coordination strategies. So that concludes the last part of my my presentation. And I'd like to show you my conclusions now. I've shown you my work in seismic hazard, and I want to remind you that the elastic rebound theory has been proposed more than 100 years ago. However, their implications are not captured usually in seismic hazard applications because the models that are proposed are hard to calibrate, and also earthquake data, or large earthquake data, is very sparse. I've proposed this model that captures this behavior, and I'll show you how to calibrate this model using a Bayesian approach that supplements the limited historical data with synthetic data. And the application to the subduction zone in Peru showed that these time effects can have impact in the seismic hazard prediction by a factor of 4. And I've shown you also that the synthetic data can be effective to reduce parameter uncertainty by a factor of 2. And this information can trigger additional variations in the seismic hazard almost by 40%. So as part of this, the emergency response part, I show you what are the key features of an emergency response. There is high demand of healthcare, reduced capacity, and there is a system behavior in a large urban center. I've shown you a formulation to capture these critical features in a large urban center, and how to leverage optimization techniques for these emergency plans. So the application shows that in Lima, after a magnitude 8 earthquake, we're going to have almost 5,000 people that are going to need surgical procedures. Unfortunately, 50% of the operating rooms are going to be out. Yet it pays off to have high coordination policies, because if you implement them, as the results show, you can reduce waiting times by a factor of 3, and that can have implications in saving lives after a disaster. So I've highlighted my contributions in the seismic hazard. You can find a little bit of that, or more descriptions on that in a couple of publications here. The same with the emergency response part. In addition, I didn't went into detail, but I told you I extended a PV framework to a regional level to to model earthquake casualties with computational efficiency, and that leads to better estimations of casualties as compared to often used methods like payer when data is sparse or not recent in countries. And finally, in the last part of my PhD, I've been working on distributed energy resources and coupling disaster analytics and solar generation to see how this rapid increase of solar panel adoption is going to have a role in resiliency. So you can see a little bit of that also in my dissertation and in this publication here. So with that, I thank you.